Okay, so thank you for the introduction. So the general purpose of my talk today will be to explain recent progress in our understanding of quantum gravity in classes of spacetimes where the effects of gravity are very weak at long distances. And in technical terms, these spacetimes are referred to as asymptotically flat. And in particular, I'll explain the sense in which they are holographic, meaning that I'll present evidence for why they might be understood in terms of ordinary quantum systems in fewer dimensions without gravity. So the basic motivation for this research originates with one of the outstanding fundamental questions in physics, the problem of quantum gravity. And one way to articulate this problem is through the question, what is the microscopic structure underlying quantum mechanical theories that reduce to or reproduce general relativity at long distances and low energies? Now, in order to make concrete progress in addressing this question, the first thing to do is to identify the types of observable phenomena we expect to be able to predict or explain with sufficient knowledge of the microscopics. So, for example, in the case of the other fundamental forces, we test and verify our understanding of the microscopic structure by making predictions for scattering experiments or explaining their results. And in particular, scattering at high energies probes the physics at short distances and thereby reveals the underlying microscopic structure. So similarly, a satisfactory theory of quantum gravity should provide the answers to analogous experiments one might imagine performing in principle to uncover the microscopic structure of gravity. So thus, a sharp question that directly addresses the problem of quantum gravity is, what is the solution to the gravitational scattering problem? Or more precisely, what are the UV complete scattering amplitudes in a quantum theory of gravity? Meaning simply, what are the predictions for scattering at high energies in a theory of gravity? So this question will be the central focus of the talk, and our interest in it resides in the fact that it represents a concrete approach to the fundamental problem of quantum gravity. Now, we believe we have a more satisfying answer to this question for the other fundamental forces in nature. So what makes gravity special? And the technical answer is that gravity is non-renormalizable. But really what this means is that our predictions and theories of gravity break down at short distances in a way that they don't in the other theories. And in particular, as we probe shorter and shorter distances in a theory of gravity, we always expect to find new parameters, which we can think of as a proxy for new physics. And the standard techniques known as Wilsonian effective field theory do not predict the values of these parameters. So thus, from a standard approach for organizing microscopic structure, we find that a consistent description of quantum gravity involves infinitely many undetermined parameters. So therefore, another way to phrase the challenge is that in order to gain any substantial insight into the microscopic structure of gravity, we're in need of a new sort of organizational principle. Now, the lore is that there does exist a new sort of organizational principle for theories of gravity, which is that they're holographic. And specifically, this means that the physics in a theory of gravity is expected to organize like a theory in fewer dimensions without gravity. Now, there are a variety of different arguments one can give in support of this expectation, but for the purpose of this talk, since we're interested in the gravitational scattering problem, a key observation is that it is inherently holographic. And in particular, by addressing the question, what is the final state reached at late times, given a particular initial state at early times, the scattering problem only makes reference to data at the past and future boundaries of spacetime, and thus is an observable that by construction lives on the boundary and therefore in fewer dimensions. Now, of course, we typically interpret this data as related by time evolution at intermediate times or through the bulk, but this perspective nevertheless brings forth the notion that we might imagine answering the scattering problem without ever referring to time evolution through the bulk. And by definition, a theory which addresses the scattering problem in this way is holographically dual to a theory of quantum gravity. So therefore, a simple reason for expecting the holographic principle to apply to the gravitational scattering problem is because the associated observables live on the boundary. So now that we recognize that the gravitational scattering problem is inherently holographic, the next thing to ask is, why is it plausible that we might solve the scattering problem holographically? That is, without ever referring to evolution through the bulk. And the hook, or key evidence that makes this proposal plausible, is that it turns out that the scattering problem in theories of gravity is constrained by classes of infinite dimensional symmetries. Now, generally speaking, the reason why symmetries support this possibility is that they imply conservation laws. So, for example, a symmetry under time translations implies conservation of energy, which in turn implies that the initial and final states of the scattering problem are required to have the same energy. Now, since energy is an intrinsic property of an initial or final state that is determined by data at early or late times, the conservation law thus simplifies the scattering problem in a way that never makes reference to quantities at intermediate times. Therefore, an infinite number of symmetries offers the possibility of organizing the scattering problem in such a way that it might be solved holographically. So in the rest of the talk, I'll explain in more detail the evidence for a holographic description of the gravitational scattering problem and the critical role that's played by symmetries. And in particular, we'll see that symmetries both provide intrinsic structure as well as serve as a guide for how to organize the theory. So there are two main parts to the rest of the talk. And the first will focus on the infinite dimensional symmetries of the gravitational scattering problem, which are sometimes known as asymptotic symmetries. So in this part, after providing a heuristic explanation for why infinite dimensional symmetries arise in a theory of gravity, I'll explain how these symmetries constrain the scattering problem. And we'll see that the constraints from these symmetries are intimately related to known universal behavior in the infrared sector and ultimately imply that symmetry is the origin of this universality. And this will enable us to, for example, identify a universal infrared phenomena known as memory as a symmetry-protected observable. Now, it turns out that from investigating this class of symmetries, one discovers that the scattering problem in 4 dimensions admits of the local conformal symmetry of a theory in 2 dimensions. And this simple observation immediately implies that the scattering data in 4 dimensions organizes like observables of a theory in 2 dimensions with a conformal symmetry. So thus, symmetry arguments will lead us to a holographic description of 4D scattering in terms of a theory in 2 dimensions. And so in the second part of the talk, or this last part of the talk, I'll first give a physical explanation for why the conformal symmetry of 2 dimension arises, and then I'll outline the procedure for making this hidden 2D structure manifest. And finally, I'll briefly highlight a number of insights gained from reformulating the 4D scattering problem in this language. So in order to explain why the gravitational scattering problem admits classes of infinite dimensional symmetries, it's helpful to begin with a more abstract discussion of symmetries in the context of the scattering problem. So generally speaking, symmetries are transformations that preserve the laws of nature, such as, for example, preserving the equations of motion. And this implies that they map solutions to solutions and thus can be useful for generating new solutions given old ones. So if we return to this elementary example of time translations, then systems with this symmetry admit families of solutions that are interrelated by shifting the time parameter. Now, since the scattering problem addresses the question, given an initial state of the system at early times, what is the final state after time evolution? Solutions to the scattering problem take the form of pairs of initial and final states that are related by time evolution, which is often represented by the scattering or S matrix. So now if we put these two ideas together, then a symmetry of the scattering problem is a transformation that, when applied to both the initial and final state, preserves the S matrix. So explicitly, if we begin with a pair of initial and final states that are related by time evolution and therefore represent a solution to the scattering problem, then upon acting with a symmetry, we'll find a new pair of initial and final states that are still related by time evolution. And finally, as I mentioned previously, symmetries are useful in the context of the scattering problem because they imply constraints that tell us what initial and final states could possibly be related by time evolution. And again, in the presence of a time translation symmetry, solutions to the scattering problem can only ever involve initial and final states with the same energy. So now I can provide a heuristic argument for why the gravitational scattering problem admits infinite dimensional symmetries. So since the relevant and defining feature of symmetries of the scattering problem was their action on initial and final states, let's describe symmetries in terms of transformations that could be measured by observers monitoring these initial and final states. Now, if we focus on the massless scattering problem, in which the degrees of freedom are moving at the speed of light, then we can envision the region of space-time where the final state observers reside as a place that light rays reach after propagating for an infinite amount of time. Now, since light waves can propagate in any direction, this region should have a sphere's worth of directions. And it can be thought of as the celestial sphere. So in order to thoroughly monitor matter exiting the sphere, we need to populate it with a final state observer at every angle. But now let's revisit this idea of time translational symmetry, which we'll call implied families of solutions that are related by a shift in the time parameter. So suppose each observer exercises this symmetry to reset their watch. Now, since our collection of observers are sitting at different points on a sphere of infinite radius, they are out of causal contact with one another and thus unable to collectively synchronize this action of resetting their watches. So this implies that there is therefore an independent time translation symmetry for each observer, or equivalently for each point on the sphere. And since there is a continuum of points, there are an infinite number of symmetries. So thus, we found an infinite dimensional enhancement of the translation group in a theory of gravity. So these symmetries were originally discovered by the general relativists Bondi, Vandenberg, Messer, and Sachs, and they are known as supertranslations. So now that I've provided a rough idea for why there are infinite dimensional symmetries, I'd like to provide a little bit more intuition for how they transform solutions. And for this, I'm going to need to introduce a few more concepts. So in particular, on the last slide, I described the region of spacetime where we needed to place the final state observers as a sphere, but this isn't quite the whole story. Nevertheless, we can see what's missing by considering the following thought experiment. So suppose you have a light bulb that you flash at time t equals 0. Now, the light rays emitted at this time will propagate outward towards a sphere of infinite radius. So far, so good. However, now suppose you flash this light bulb again 10 seconds later. So once again, the light rays emitted at the delay time will propagate outwards towards the sphere of infinite radius, but the key observation is that it cannot be the same sphere as the one from the original flash. And the reason is that both signals propagate at the speed of light, so the second one can never catch up to the first. So what we've learned is that the region of spacetime that's reached by all outwardly propagating light rays can't be just a sphere, but rather must also include a time direction, which is usually called retarded time. So Penrose diagrams, such as the one I've shown here, can be useful for visualizing these ideas. So time increases as you move up the page and light rays move at 45 degrees. So here we can see how the light rays that are emitted from the origin at an earlier time reach a different place on the boundary than the light rays that are emitted from the origin at a later time. Now, in order to represent 4D spacetime on a 2D page, every pair of points represents a two-dimensional sphere. And points on either side of the origin, r equals 0, represent antipodal points. So now we can also see how the place that is reached by all light rays emitted at a particular instance of time forms a sphere. And since and the points on the sphere are out of causal contact with one another because they cannot be connected by a path whose slope is greater than 45 degrees. And finally, the place that is reached by light rays emitted over all times is this three-dimensional surface, which is called future null infinity. And it represents the place that we must populate with final state observers in the massless scattering problem. So with this picture in hand, let us now revisit the supertranslations. So first recall that supertranslations were independent time translation symmetries for every point on the celestial sphere. But now suppose we begin with a solution in which there is a burst of radiation at the North Pole and the South Pole at retarded time t equals 0. Now, using an ordinary time translation, we can map it to a solution in which both bursts are delayed by 10 seconds. Or we could map it to a solution where they're both delayed by an hour, or really any other amount of time, the relevant point being that any solution obtained by acting with an ordinary translation will always have the bursts coming out at the same time. Now, on the other hand, if we act with a supertranslation, then we can relate the solution in which both bursts come out at retarded time t equals 0 to a solution in which only one, say the one at the South Pole, is delayed by 10 seconds. So that is to say, generic supertranslations do not preserve the synchronization of events at different points on the celestial sphere. But now that we've identified an infinite dimensional enhancement of the translation group, from our general discussion, we expect these symmetries to imply an infinite number of constraints on the scattering problem. And moreover, since these symmetries are local enhancements of the translations, we might anticipate that the associated conservation laws are related to local enhancements of energy conservation. So in order to see this, we're going to take a slight detour. And in particular, we're going to start with an apparently entirely different aspect of the gravitational scattering problem, and once again arrive at the conclusion that it admits an infinite number of symmetries. And then at that point, we'll identify those symmetries with the supertranslations. So our starting point will be a universal feature of the gravitational scattering problem known as a soft theorem. So soft theorems historically originate from a quantum field theoretic analysis in which the initial and final states of the scattering problem are organized in terms of particles. So in this context, the scattering problem is phrased as the question, given some set of particles with certain amount of energy and momentum at an initial time, what are the particles found at a late time? And the solution to the scattering problem takes the form of scattering amplitudes. So soft theorems are then a universal relationship between a scattering amplitude for the emission of the massless particle in the limit in which that massless particle's energy is taken to zero, and a scattering amplitude without that massless particle. So scattering amplitudes are typically very complicated, and it's rather remarkable that such an exact relationship exists. And the standard explanation is that low energy particles only probe long distance physics and thereby capture universal aspects of the scattering process. So thus these relations are typically understood as reflecting the universality of infrared physics. However, recalling that symmetries of the scattering problem interrelate pairs of initial and final states, it's natural to suspect that such an exact relationship may in fact be the consequence of a symmetry. And indeed, this turns out to be the case. So in order to see this, let's begin with Weinberg's soft graviton theorem, which is a statement pertaining to scattering processes in which a graviton is emitted. So here we're going to find it useful to parameterize this graviton momentum in terms of an energy and a unit 3 vector, which we can think of as specifying a point on the surface of the sphere. So then the statement of the theorem is that the scattering amplitude for the emission of a graviton develops a pull in the energy of that graviton in the limit in which the energy is taken to zero. And moreover, the residue of that pull, which can be extracted by multiplying by the energy and taking it to zero, is universally given by the scattering amplitude without that soft graviton multiplied by a number which is known as the soft factor. So the soft factor is a function of the direction in which the soft graviton propagates, its polarization, and the momenta of the other particles participating in the scattering process. So as I mentioned previously, this relationship among scattering amplitudes is typically regarded as a statement of universality that arises in the infrared sector, since it pertains to the scattering of a low energy graviton. And in particular, the ways in which it is universal is that this soft factor is independent of the precise theory. So specifically, it only depends on the momenta of the external particles, but none of their other quantum numbers. And moreover, it takes a universal form for each particle. In other words, there's the same contribution for each particle. So now I'm going to explain how this exact relationship between scattering amplitudes can be understood as the consequence of a symmetry, which also provides a simple explanation for these universal aspects. So the first step is to regard this soft factor as the eigenvalue of a single particle state under the action of an operator, which we denote QH to signify a hard charge, that implements a transformation, delta, that depends on the direction, theta phi, towards which the soft graviton propagates. So then this right-hand side can be interpreted as the net transformation of single particle states that comprise the scattering state under the transformation delta theta phi that is generated by this hard charge. But then the soft theorem can be interpreted as a statement that the S matrix is invariant under the transformation delta theta phi of single particle states, provided that a soft particle is added. So with this interpretation in mind, let us introduce a second operator, which we denote QS to signify a soft charge, whose role in life is to add soft gravitons to the scattering state. So then the left-hand side can be written in a similar form as the right-hand side, And upon rearranging the soft theorem by bringing both to one side, we arrive at the statement that the S matrix is invariant under a symmetry generated by a charge Q, which is given by the sum of the hard and the soft charges. Now, since we can repeat this argument for every direction in which a soft graviton can propagate, we conclude that the S matrix is invariant under an infinite number of symmetry transformations, which are labeled by the point on the sphere associated to the direction in which the soft gravitons propagate. Now, in order to see why this set of infinite dimensional symmetries are equivalent to the supertranslations, it's helpful to parameterize the symmetry by an arbitrary function rather than points on the sphere. And upon doing so, we find that the eigenvalue of a massless single particle state under the action of the hard charge is now given by the energy of that particle multiplied by the function evaluated at the point on the sphere towards which this massless particle is propagating. So in other words, we find that the hard charges parameterized by functions act locally on massless particles, meaning again that their action only depends on the value of the function at the point on the sphere associated to the direction of the particle on which they act. So now with this local action, let's consider the case in which this function is constant and equal to 1. So then the eigenvalue of the hard charge is just the energy of the particle on which it acts. But we know that a transformation of a momentum eigenstate that returns its energy is just an ordinary time translation. So therefore, we can identify the symmetry transformation when f is constant as generating an ordinary time translation. On the other hand, when f is a generic function, then the eigenvalue is the energy multiplied by the, it's the energy weighted over the sphere by this function f. So hence, the symmetry transformation for a generic function generates a translation that is weighted over the sphere by that function. Now, since f was an arbitrary function on the sphere, this implies that there is an independent time translation symmetry at every angle. And moreover, we learn that the hard charge is characterizing the local energy flux at every angle. Now, from our study of the soft theorems, we found that the conserved charges were given by the sum of the hard and the soft charges. So therefore, the conservation laws that are implied by the supertranslations involve energy flux at every angle through the contribution of the hard charge, but are statements of conservation only upon including the addition of the soft charge. And as such, the physical significance of the soft charge is crucial to fully appreciate the way in which supertranslations constrain the scattering problem. So to this end, let's revisit the soft charge. So from the previous analysis of scattering amplitudes, we obtained an expression for the soft charge in terms of creation and annihilation modes of zero energy gravitons, with an extra factor of omega to pick out the pole. Now, if we write this instead in terms of field operators, then this factor of omega turns into a time derivative, and we can identify the soft charge as giving the zero frequency component of the first time derivative of the radiative gravitational field. So therefore, at the classical level, the conservation law constrains the zero frequency component of the radiative gravitational field. So with this phrasing, the soft charge sounds a little physical. In particular, it sounds as if the data in the soft charge is something that can't really be measured. However, this is just poor phrasing because if we take omega to 0, then we can identify this integrand as being a total time derivative. And thus, the zero frequency component is actually equivalent to a net shift in the gravitational field, or the metric in time. And essentially, this is nothing more than the observation that the Fourier transform of a pole in frequency space is a step function in time. So thus, the soft charge is capturing a permanent shift in the asymptotic metric. Now, remarkably, it's been known since the 70s precisely how to measure such a net shift in the gravitational field. It just hadn't been identified as part of the scattering data that's constrained by supertranslations. So on the right here, I've included a clip from a paper by Baginski and Thorne in 1987, in which they present a formula that relates the net change in the asymptotic metric to what in hindsight we can recognize as the soft graviton factor from Weinberg's soft theorem. So Back in 1974, Zeldovich and Polnareff gave the original explanation for how a pair of inertial observers could measure this permanent shift in the metric. And so the basic idea was to consider the effect of a burst of gravitational radiation on the trajectories of the pair of inertial observers. So before encountering the bursts, the pair will remain at fixed relative separation from one another. As they pass the gravitational wave, it will cause the distance between them to oscillate, but after they've traversed it, they will again find themselves at fixed relative separation from one another. However, the key observation is that this final displacement need not be the same as the original displacement before encountering the burst. And the permanent change in their relative displacement is something called gravitational memory. And so the upshot is that the net change in their relative displacement is directly related to the permanent shift in the asymptotic metric that was induced by the burst of radiation. So the precise mathematical relation between the change in their relative displacement and the change in the asymptotic metric can be derived from the geodesic deviation equation in general relativity. But the key takeaway is that the contribution from the soft charge is capturing a permanent shift in space-time that inertial observers can detect through changes in their relative displacement. And so indeed, by tiling the celestial sphere with inertial observers and measuring the change in their relative displacement, one could in fact fully reconstruct the contribution from the soft charge at every angle. So thus, the conserved quantity implied by supertranslations is the local energy flux at every angle together with this permanent shift in spacetime. So at this point, let me summarize what I've explained thus far and highlight the significant lessons. So the key idea I presented was the gravitational scattering problem is constrained by infinite dimensional symmetries. And I justified this idea by two different approaches. First, from examining the causal structure of spacetime, and then from studying a universal feature of scattering amplitudes known as the soft theorem. And specifically, we identified a class of symmetries that were an infinite dimensional enhancement of the translations and found the associated conservation laws constrain the energy flux at every angle together with a permanent shift in spacetime. And this permanent shift in spacetime induces a measurable effect on the trajectories of inertial detectors. Now, a crucial aspect of this analysis was that universal behavior in the infrared could be interpreted as consequent of symmetry. And in fact, the key insight to be gained is this broader idea that symmetry is the origin of universal behavior in the infrared. So to that end, it's worth further investigating this relationship between infrared physics and symmetries. So a general feature common to both is that both are often the origin of universal phenomena. So the intuition in the infrared sector is that low energy probes are insensitive to the non-universal details that appear at short distances, while the intuition in the presence of symmetries is that symmetries protect observables from depending on non-universal specifics of the system. Now, there's no general reason why universality in the infrared is or should be equivalent to universality due to symmetry. So in order to understand how these ideas might apply more generally, it helps to uncover the root of the equivalence. And so one way to understand it is as follows. So suppose you have a conserved charge that generates a continuous symmetry. Well, then you can write it as a spatial integral of the zero component of the Noether current. But if you interpret this as an integral as a Fourier transform, then you notice that the charge is really picking out the long wavelength data of the current density. So therefore, morally, the root of the equivalence is that conserved charges are telling us about long wavelength data. So now, since rather general logic underlies this equivalence, it in fact readily generalizes to other contexts. So in particular, this equivalence allows us to use known universal behavior to discover new symmetries. So for example, scattering amplitudes in quantum electrodynamics involving the emission of a low energy photon are also known to emit universal behavior. And just like Weinberg's soft graviton theorem, these soft photon theorems can be interpreted as statements of invariance of the S matrix under an infinite dimensional symmetry. And thus, the known universal behavior encapsulated by the soft photon theorem led to the discovery of an infinite dimensional symmetry of quantum electrodynamics, which has come to be known as large gauge symmetry. So likewise, in non-abelian gauge theory, the known soft gluon theorem led to the discovery of non-abelian large gauge symmetries. And finally, the generalization of Weinberg's soft graviton theorem and gravitational memory to gravity in higher dimensions led to the discovery of infinite dimensional symmetries in gravitational theories in higher dimensions. Now, the full power of the equivalence allows for discovery in the converse direction as well. So in particular, we can use a known symmetry to discover new universal phenomena. So for example, in the context of non-abelian gauge theory, we use the large gauge symmetry, which, as I mentioned on the previous slide, was discovered from the soft gluon theorem, to establish a new universal infrared phenomena known as color memory, which is just the non-abelian gauge theoretic analog of gravitational memory. And moreover, we even identified its relevance for scattering experiments carried out at particle colliders. Now, in addition, known symmetries can be used to provide new insight or explanations for known universal infrared behavior. So, for example, the large gauge symmetry in quantum electrodynamics can be used to explain the known property that scattering amplitudes factor into a universal piece containing all infrared divergences and a piece that is infrared finite. And likewise, gravitational scattering amplitudes also admit such a factorization, which can be explained by the supertranslation symmetry. Now, it turns out that the infrared divergent piece in both of these factorizations is formally zero. Nevertheless, it's possible to construct infrared safe scattering amplitudes in both gauge theory and gravity, in which the zero factor has been canceled to give a finite result. And the underlying principle for constructing such infrared safe scattering amplitudes is in fact large gauge symmetry and supertranslations.
So, Monica, may I ask about previous slide?
Yes.
So can you say a few more words about this non-abelian color memory? Because in non-abelian case, there is no true IR limit, right? Because there are no massless gluons. There is a mass gap at the end of the day. So how does it work?
Right, so it turns out that there is a particular limit of scattering that a classical description applies. And so essentially, well, this picture arises at distances that are short in comparison to the confinement scale. So everything is deconfined. That's an important point. And yeah, I think that that's probably most directly answers your question.
But is there like sharp statement about like really physical S matrix, which would be S matrix of massive states and not partons?
Well, in order to have a memory effect, or memory effects, the probes in those associated to memory effects have to be charged under the symmetry. So if you are interested in a color memory effect, your probes have to be charged, carry color charge. So you have to be working in a limit in which it applies in a limit where you have some knowledge of the fact that it is carrying a color charge. So you can't just talk about neutral particles.
Thanks.
Okay, so I just spent the last several slides sketching a variety of ways in which the story of supertranslations generalized to other contexts, when in fact the most simple generalization one could imagine is an infinite dimensional enhancement of the rotations. And indeed, in theories of gravity, there is an infinite dimensional enhancement of rotations as well as boosts, since these theories are relativistic. And this class of symmetries is called superrotations, and they also follow from a type of soft theorem. So it turns out that scattering amplitudes involving the emission of soft graviton do not just admit universal behavior at leading order in the energy of the graviton, but also at subleading order. So previously, we saw that the supertranslations followed from the universal behavior associated to a pole in the graviton energy. And it turns out that these superrotations follow from the universal behavior in the first subleading correction, or in other words, the order 1 part of the graviton energy. But what's really remarkable about the superrotations is that this infinite dimensional symmetry has appeared before. And so in particular, it can be identified as the local conformal symmetry of theories in 2 dimensions, which is sometimes called the Virasoro symmetry. So what this means is that the scattering data in a 4-dimensional theory of gravity organizes like observables of a theory that lives in 2 dimensions. So thus not only have the infinite dimensional symmetries provided intrinsic structure to the scattering problem through an infinite number of constraints, but they have revealed where the holographically dual theory might live. Namely, it is the theory that lives in these two dimensions, the two dimensions in which this conformal symmetry acts. So with this in mind, let me provide a little more intuition for why we found the conformal group of a theory in 2 dimensions as a symmetry group of scattering in 4 dimensions. And this will then help us understand where to find these hidden 2 dimensions. So let's begin by considering a massless particle that travels in the z direction, or equivalently, whose spatial momentum is directed towards the north pole of the unit sphere. So we can always write the form momentum of such a particle in this way. So now let's consider how this momentum transforms under a boost in the z direction. Now, under such a boost, it will still point in the z direction, so without loss of generality, we can write the third component as being proportional to the original third component. And since it's massless, p squared is 0, so this fixes the time component to also be proportional to the original time component. So thus, a boost in the z direction acts on a form momentum pointing in the z direction by an overall rescaling. But now we can simply rotate this story to apply to an arbitrary direction. So specifically, as before, we can parameterize the momenta in terms of an energy and a unit vector that points to an arbitrary point on the unit sphere. And then under a boost in that direction, we again find that the momentum transforms by an overall rescaling. But now notice that since this unit vector can be associated to a point on the sphere, a boost in that direction rescales the unit vector and therefore acts as a dilation on the sphere. Now, since boosts or symmetries are relativistic theories, and our theory is relativistic, this implies that the dilations of this 2D sphere are symmetries. And therefore, the surface of the sphere can be identified as the 2 dimensions in which the holographically dual theory lives, and these dilations can be identified as part of the conformal group. So now that we have some intuition for how the scattering problem emits the conformal symmetry of a theory in 2 dimensions, let me explain how to exploit it. And the strategy will be to make the scattering amplitudes resemble observables of a theory in 2 dimensions. Now, since this conformal symmetry was the foundation of this 2D structure, the way to make the scattering amplitudes resemble observables in 2 dimensions is to make the conformal symmetry manifest. And the basic idea for doing so is to scatter states that diagonalize the dilations in 2 dimensions. Now, standard scattering states are labeled by the momenta of massless particles, or for standard scattering states for massless particles are labeled by their momenta. And as we saw previously, the momentum of a massless particle gets rescaled by the boosts that we identified with these dilations in 2 dimensions. And in particular, we can identify the differential operator that generates the boost and verify that it acts non-trivially on these massless momenta. So therefore, standard scattering states are not invariant under 2D dilations, or equivalently, they don't diagonalize these transformations. And of course, they instead diagonalize translations, which is why they're labeled by momentum, the eigenvalue under a translation. So therefore, the states that will diagonalize the 2D dilations must be boost eigenstates. So the strategy for constructing such states will be to identify the integral transformation that diagonalizes the generator. So for example, the generator of translations is diagonalized by a Fourier transform. So we can obtain translation eigenstates by constructing states of definite momentum by performing a Fourier transform. Now it turns out that the so-called Mellin transform diagonalizes the generator of boosts, and thus we can construct states of definite boost weight by Mellin transforming momentum eigenstates. So the takeaway is that scattering states which diagonalize the 2D dilations are boost eigenstates and accordingly are labeled by boost weight, which is the eigenvalue under the 2D dilations. And these states are related to the standard momentum states by a Mellin transform with respect to energy, and thus they involve a superposition of all energies. So now it turns out that a variety of new insights into the gravitational scattering problem arise from studying these scattering states. So first, it was not a priori obvious that soft theorems, which in momentum space characterize the low energy behavior of scattering amplitudes, need take any simple form for the scattering of boost states, which are of indefinite energy. Nevertheless, they do in fact have simple avatars, which are called conformally soft theorems. And these can be thought of as simply a manifestly Lorentz invariant presentation of soft theorems that circumvents a non-Lorentz invariant reference to factors of energy, and thereby further elucidates their connection to symmetry. So next, in this framework, it turns out that one can use the symmetries to fix a so-called operator product expansion coefficients, which are basically characterizing interactions between different particles. And what's particularly novel is that none of the particles participating in these interactions need be soft. So in this language, the symmetries are in fact constraining more than just infrared interactions. So another key result is that there is a canonical prescription for curing infrared divergences that set all exclusive scattering amplitudes to 0. So previously I had mentioned that the symmetry constraints were the guiding principle for constructing infrared safe scattering amplitudes. But in momentum space, there's no uniquely preferred construction, while in boost weight space there is. Now next, tying back to the beginning of the talk, a goal was to find a new organizational principle for the gravitational scattering problem. And here we find that the boost weight scattering amplitudes do in fact organize the symmetry in a new way. So in momentum space, scattering at low energies is insensitive to the details at high energies, but for boost eigenstates, there's no such decoupling, essentially because the boost eigenstates involve contributions from arbitrarily high energy. And finally, the 2D conformal symmetry actually organizes symmetries associated to soft theorems in a particularly nice way and gives rise to a very interesting and powerful symmetry algebra. Okay, so let me summarize. So I began by introducing the scattering problem as a central element to our understanding of quantum gravity. And then I explained that the gravitational scattering problem admits infinite dimensional symmetries whose constraints take the form of soft theorems. And this led to a powerful insight that universal behavior in the infrared could be precisely equivalent to universality due to symmetry, which in turn led to the discovery of new symmetries in universal phenomena. So among these was the pivotal insight that the gravitational scattering problem admits the local conformal symmetry of a theory in 2 dimensions. And this observation inspired the idea that scattering in a 4-dimensional theory of gravity might be holographically dual to a conformal theory in 2 dimensions. So to investigate this proposal more seriously, we made the scattering amplitudes resemble observables of a 2-dimensional theory by making the conformal symmetry manifest. And specifically, we identified boost eigenstates as the class of states that transform simply under 2D dilations and thereby made the conformal symmetry manifest. And finally, I listed a number of new insights into the gravitational scattering problem that were obtained by studying the scattering of boost eigenstates. So this new reformulation offers a host of new tools for the gravitational scattering problem that are standardly used in studies of 2-dimensional conformal field theories. And these tools motivate new types of questions that are novel from the perspective of gravitational scattering, but quite natural from the perspective of a conformal theory. And conversely, the scattering amplitudes give rise to exotic new structures from the perspective of a 2-dimensional conformal theory. But of course, since these structures originate from scattering amplitudes, they carry intrinsic physical significance and thus are a source of new interesting questions for conformal theories. So thank you.
Thank you very much. Very nice presentation. And now it's time for questions. I see that a question from Sergey.
So thanks for the very nice talk. So how I'm supposed to think about this absence of decoupling? Is it a good thing or a bad thing? Because physically decoupling is there, right? So in other words, maybe one can discuss like in gravity, things are a bit different, but I can also play the same game in quantum field theory and go to boost eigenstates. And then again, decoupling will be obscured, but we know it is there. So so what is the right way to think about that?
I think there's 2 answers. So one thing is that there's a question of, we like the fact that we standardly like the fact that there's decoupling because that's how we make predictions, right? We know that we scatter things at low energies and there's only some number of parameters that we need to keep track of. And there's a question of whether you can actually recover this directly from the boost eigenstate space. And the answer is you actually can. There's a procedure where you can explicitly without going back to momentum space, you can explicitly recover the effective field theory expansion. I think then you would also say that you like this because there are certain the special thing about gravity is that you have an expectation for what happens at very high energies, which is that, naively, well, in simple terms, that if you scatter things at high enough energies, you'll eventually form a black hole. And so that's something that you want, that you have a physical argument for why you think should happen, but from a momentum space perspective where you're just sort of adding more and more terms that become important at higher energies, it's hard to see how you get that result out. And so part of the thing about talking about it in this new language is that actually that's another constraint that you can implement in a simple way.
Mm-hmm. Thank you.
Other questions? Since I don't see any, let me ask one. How large is infinity in this argument? I mean, Sergei asked the question about scattering amplitudes in chromodynamics, where there is a cutoff, but you're talking about infrared problems. But more generally, there is a universal technical fact in this infrared physics, and it's that the commutators of your infrared operators have a discontinuity at the boundary of null-infinity. So the commutators of the soft graviton or of the soft photons are not the limits for, say, retarded time going to plus or minus infinity of the commutators of fields at finite time, right? So, but on the other hand, in the theorems that you explained, you take a limit, right, the soft limit. So how these two things are in agreement? The fact that you have a discontinuity in some commutators, precisely those involving the infrared quantities, and the fact that we want to take limits for low frequency. So maybe I want to make it a little bit more concrete. When you measure memories, they are always finite because you have a finite time to measure where your probe was at the beginning and where it ended up after some time t. On the other hand, the probes could go back to the same position very slowly, right? So after you have stopped observing them, they can revert back to the original position so slowly that essentially you spend no energy in putting them back from where they were at the beginning, and then the total memory at true infinity would still be zero, right? There would be no displacement. So in a sense, how do you take into account this this fact, and how do you formulate theorems that are valid for finite time in terms of this infrared theorem?
So I think that maybe the thing to say is that the symmetry that you're referring to controls a pole in the energy at zero. And that's something that, if you think about the effect it has in the time domain, that is, the effect in the time domain is the permanent shift. So it doesn't really, other things can happen, but those are not the things that are protected by symmetry.
So, but would I be able to predict what a particle of energy that is much smaller than, say, the typical scattering energy in a process do using soft theorems? And if so, I mean, why? I mean, there must be some notion of continuity in the energy, even though certain quantities seem discontinuous, right?
Right. So good. So right. So I haven't worked this out in detail, but what I would suspect is that, you know, many ways of stating the soft theorems are statements where they say the energy you're taking soft is soft in comparison to all the other energies participating in the scattering process. And so roughly speaking, I think that there needs to be some separation of scales where, you know, you can roughly think of how big your scattering region is as being set by essentially, you know, your center of mass energy. So things that are higher center of mass energy have smaller scattering regions, roughly. And you need your things that are low energy. So that sets some scale, and things need to be, you need to be looking at much lower energies than that distance, or sorry, much lower energies than that energy, or in other words, longer distances than that scale. So like, for example, you know, classically you can show that the electric field that is, you know, constrained by the symmetries or protected by the symmetries for point particles is exactly what you get if you had just taken point particles, sent them all at the origin with some fixed velocity and had them come out at the origin at some other fixed velocity, which you could think of as an idealized scattering experiment where the scattering region is of 0 size. And that perfectly gives you basically Weinberg's prediction for the gravitational radiation. So you simply need to be in a limit where the wavelength you're looking at is much larger than this scattering region.
Sorry, go ahead. Just trying to understand. Like, let's consider gravitational scattering at very high energies, at like Transplanckian energies, such as black hole forms. Then, yeah, like, there are several scales. We may take frequency much smaller than the energy of initial particles. We can take it much smaller than Planck scale, or we can take it much smaller than the temperature of Hawking radiation of a black hole which is formed. So,
yes. So I didn't, right. I think the precise statement is that you probably want to, I would say you need to work at fixed angles and probably center mass energy to infinity. That would be like, I mean, yes, there's a lot of different.
But so in this context, soft means what? Which of these three, right?
Oh, sorry, what were the options that you gave?
Well, they're just much softer than the energy of colliding particles, much softer than Planck scale, or much softer than Hawking temperature of the black hole, which would be formed in the collision of these particles.
Right, I would say much softer than the momentum of the incoming particles.
Okay, interesting. So then from the point of view of the scattering process, that's kind of very hard particles, right? Because the typical emitted particle would be Hawking quantum. But, right?
Yeah, so, but I think that that's the right.
Interesting. Okay.
We have questions. Any? I know that students will also have. Oh, I see Glenys.
Thanks, Monica, very much. It's a really elegant presentation. I'm still trying to get my head around whether this is should be thought of as a insight into why, for example, there's holography and so on. That's how I was sort of mainly taking it, or whether it's a sort of practical avenue to address things. And so I thought maybe asking you about the non-abelian case is more my lowbrow territory. And I can't think of, I mean, so you answered to Sergey that the color memory, you had to specify a colored state, but you can't do that, right?
Right.
Or at least I don't think you can. So does it actually have any meaning? I'm on a little bit of a perilous ground of whether there's actually anything like predictive about this. Like, is the color memory correspond to some phenomenon?
Yeah, let me explain it in more words. So the color memory is supposed to be a direct analog of the gravitational memory. And so the idea is that if you did, for example, a deep inelastic scattering experiment where you probed a heavy ion by setting an electron at it, right? So they interact by the electron exchanging a photon, and that photon can dissociate into a pair of a quark-antiquark pair. And so the analog is supposed to be that the quark-antiquark pair are the analogs of the inertial detectors, and as they traverse the heavy ion, it causes their colors to rotate, just as the positions of the inertial observers would oscillate. And after they've traversed the heavy ion, the point is that while they were initially in a singlet configuration, they need not necessarily be in singlet configuration anymore. Now, if you wanted to do the—
You don't mean, when you say a singlet configuration, overall singlet.
Overall singlet, because they
color,
a photon, right? So they were originally a color neutral pair.
Right. And you're saying they will no longer be color neutral? That's surely not right.
No, because they've interacted, they've gone through essentially the bath of the gluons that represent the heavy ion they're probing.
Okay, fine. So it's not a heavy ion that's left because that's color neutral. It's right. Some other complex configuration, including the quark-antiquark. But what good does that do you? I mean,
right. So let me say, so if you wanted to say, I want the direct analogy of the gravitational memory effect, well, then you would say oh, I want to know essentially the relative color rotation that my quark-antiquark pair has attained. Like they were originally in a color singlet and now they have some relative color rotation, right? And of course, that's not something we can actually measure. But instead, the way to think about it is that if you imagine doing a bunch of these different experiments, you can think of essentially there is a characteristic distance over which the color fluctuations become large and they attain they attain enough color rotation that their colors are no longer correlated. And this distance is used in the nuclear theory community, and it's called the saturation scale. So essentially we identify, and so you should think of it as basically the distance. Okay, one way to say it is it's the distance over which color fluctuations become large, but another way to say it is that it's the distance over which there's some appreciable memory effect. And that is something that it does appear or is predicted to appear in observables.
Well, I guess what I'm failing to get is what this, calling it color memory, what does that teach us? Or is it more that it's supposed to teach us about the gravity? Because we can, I'm a little bit lost as to where this all leads us.
Okay, so I mean, I would say the color memory thing was, well, originally it was just to understand, more theoretically, like if you were to work in a classical Yang-Mills theory, what the analog would be.
Okay.
We happen to find that basically through looking through some literature, we realized that this effect was actually something that people were talking. We didn't think originally that it was going to be something that was something that that actually happened at particle colliders. We happened to find that it was. And I think, it's not something that I work on on a daily basis, but part of, an interesting, I think, follow-up on that is that, so there's actually a analog of the super rotation symmetry that I mentioned at the very end, which in the case of gauge theory is telling you things that are charged under it carry both angular momentum and color. So it's telling you something about correlations between angular momentum and color. And sort of the structure allows us to there should also be essentially a memory effect associated to those, and that is something that, you know, should tell you something about correlations of color and spin or angular momentum in a nucleus. And I think that would be like an interesting thing to work out. So that would be something new that hasn't been, you know, that would be something new.
Okay.
Thank you. I see Ken.
Yeah, thank you, Monica. So as sort of a follow-up on Glennis's question, so in your talk, you showed how you can interpret or reformulate existing results using the celestial amplitudes, but and find interesting connections. But so you mentioned here, you know, now you have new tools at your disposal. So is there are there things you can learn, you know, let's say by using known things within conformal field theories to learn some new previously unknown things about 4D theories of any kind? I mean, what do you think is the most promising avenue in that regard?
Well, so some things which I know have been are in the works, not anyway, is so like a common question. So a common question in 2D conformal field theories is to do a conformal block decomposition, which is that if you have a 4-point correlation function, you can, so conformal field theories are supposed to be, the structure is like the spectrum and the operator product coefficients, and that you're allowed to basically, if you have some endpoint function, you can always replace it with, you can replace two operators by their operator product expansion. And from this, you can decompose 4-point correlation functions into a conformal block expansion. And essentially, what I should say is it's a different way of taking apart a scattering amplitude. And it turns out that if you do this for example, a massless scalar contact interaction, then what you end up finding is, maybe really back. So scattering amplitudes in the normal way of thinking about them, the way you take them apart is you do things like unitarity cuts. So you ask, what are the intermediate particles that were produced? You know, I look at my asymptotic states, what were the intermediate particles? This offers a different way of taking scattering amplitudes apart. And one thing that's been found is that actually, if you study a scattering amplitude of massless scalars, then you find massive exchanges when you take them apart. And so you've taken it apart in a different way, but you've also found some sort of particles that are unusual from this perspective you would have normally thought. The other thing is that like, conformal field theory is well, one thing that's been useful is that people have been able to use the symmetries to essentially derive differential equations that they understand then the correlation functions are solutions of. And so likewise here, essentially there are many different analogs of these soft theorems, and they imply some sort of sets of differential equations that scattering amplitudes should obey. And so it's sort of a new mathematical tool.
Thank you. Yeah.
Well, actually, let me go back to Sergei's question. Let me rephrase it more generally. If you have a scattering process in which the energy of the incoming particles is much higher than the final particles, right, then what is soft? Because, okay, in the example of Sergei, you had two particles that collide, form a black hole, and decay through Hawking radiation. So you have two initial particles of very high energy, 10 to the 80 particles in the final state with very low energy. At LHC, actually, most of the processes are less extreme, like that. You have two protons colliding, a lot of pions coming out. So in that case, what is the energy that decides what is hard and what is soft? Is the initial energy of the particles or is the final energy of the particles?
Yeah, there I would say it's the final energy because, well, I would say yeah, I would say well, really you want it to be something more like the time scale under which those particles now look like they're moving on inertial trajectories. Right, like that they're no longer undergoing interactions.
Well, that's even yet another scale. That's kind of the Hawking evaporation time, right? That's even much longer scale.
Because I thought that at least perturbatively, you want each leg to be much more energetic than the photon being emitted. So.
Yeah, but I'm saying that because, like, if you think well, I'm saying this because, right, if a particle is moving on an inertial, is emitting a low energy photon such that it's basically, it's a low enough energy that it's not being knocked to a different momentum, right? It looks like it's moving on an inertial trajectory. That's why I said it that way. But I mean, I think the real answer is that it's also just a subtle question, especially in 4 dimensions, because the like Coulomb field never does fall off. And so yeah, but I think, you know, if you're forming a big black hole, the question, you know, there's the question of, are you looking at the scattering process of colliding a bunch of things and regarding the black hole as your asymptotic, your final state, or are you waiting for it to evaporate and then regarding those quanta as your final state? And those are, I think, should be regarded as 2 different processes.
I was thinking about something less exotic, like an LHC collision where you have 2 initial, say, protons that produce a lot of pions, because that's what happens most of the time, right?
Well, to be honest,
that's less exotic.
I think, right. Well, I mean, yeah, so, right. Things like soft theorems apply when the energy of the thing that is soft is much softer, is much less than the energy of the other things that are participating in the scattering process.
So in that case, you say it's the minimum energy that determines, of the products that determines what is soft. I mean, the minimum energy of, say, the charged particles for electrodynamics. You have two charged particles that collide and produce final particles that are also charged, and then the energy of the soft photon. I think at least that would be my answer.
Yeah.
Now, let me see if there are other questions. At some point, I will have to end the discussion and just ask everybody to thank you again, because you'll have a meeting with students very soon. Right? I think. So maybe we can end here and left other questions for the students. So thank you again. And I will see you tomorrow and probably other people in the audience too. Thank you. And
Thank you.
I think that you
Good
have
night.
good night.
Thank you.